Hi, my name is Leah Briscoe, and my project is on detections of inversions in the human genome. So an inversion is a segment of DNA that has been broken off in two places and reinserted into the chromosome in the opposite direction. These nucleotides are in reverse order when compared to the genome typically representing that species. So in humans, we find inversions in about 2% of individuals, and it's most common in chromosome number 9. There's two types of inversions. There's paracentric, which happens on one arm of the chromosome, and there's the pericentric inversion, which includes the centromere. So in individuals that have pericentric inversion, their children are more likely to have a deletion duplication chromosome, and that results very often in stillbirths. However, for the most part, inversions have a very unclear role in human disease, and we have yet to understand how much these inversions affect disease. Current improvements in paired and read sequencing have allowed us to make better analysis of inversions. Inversions in the human genome tend to range from several hundreds of nucleotides long to several megabytes, megabases long. So the computational problem we have here is detecting inversions based on reads given to us by a sequencer, mapping these reads to a reference, and detecting the differences between the donor sequence and the reference sequence. The output form consists of the inversion nucleotides and the location in the reference. The way that we're scoring the accuracy of the output is the F1 score. So the brute force approach to finding inversions is lower bounded by polynomial time complexity. It would involve comparing every segment of the genome, depending on your k-mer length, to the reference and inverting that segment to see how well it matches to the genome. But it has to be a perfect match in order to count as an inversion. And inversions vary greatly in length. In the simulator, we have a smaller range than reality. It's a length of 20 to 200. However, another problem is palindromes might be detected by our algorithm because those are the same in both directions, but they are not true inversions because they are exactly the same in the reference and the donor. So the baseline algorithm uses SNPs to estimate the rough range of where these inversions are, because we expect that regions that have inversions are going to have more mismatches. So using the basic aligner algorithm we've been using in this class, in the starter code, I use the list of unfiltered SNPs to come up with several ranges for where we can look for our inversions. And I use a filter that only takes groupings of SNPs that are within 10 nucleotides of each other. So I'm looking for the most dense regions of SNPs, single nucleotide polymorphisms. So after obtaining each boundary for the potential site of the inversion, I invert the sequence to count how many mismatches there are. And one by one, I will alternately remove the start and end nucleotides until the alignment is perfect. If the segment is cut down to a length less than 15, I break out of the loop. Or if the length exceeds 200, I also break out of the loop. And so those segments will not be added to my list of inversions. There are several ways this algorithm could be improved. First of all, it's very strict, and it detected far too few inversions. Also, SNPs isn't necessarily the best way to detect inversions. There's a possibility that a long portion of the inversion is very similar, like several A's long or several T's long. Yet the whole entire thing might be an inversion. Also, the way that this algorithm found the range of inversions was by slowly restricting the region instead of expanding. It only went in one direction. So an improved algorithm would go in both directions, probably using some kind of dynamic programming method. So the improved algorithm is more seeks to improve accuracy by hashing the reference into k-mers of length 8. So it uses only the region specified by the previous method, which was using snips to restrict my range. So within that region, I will hash the reference. Then I look for where the several k-mers in the donor within that same range correspond to the reference. So using that index, I can calculate exactly where a k-mer length 8 matched perfectly when inverted in the donor and compared to the reference. So once that range is obtained, I see if I can expand the size of the inversion to find the maximum length of the inversion. So overall, the methods worked well in improving accuracy. However, for the shorter genome, 10 kilobase pairs, it wasn't as the difference isn't as obvious because there were only 4 inversions in the genome to be found. However, in the longer million base pair genome, there were about 13 inversions to be discovered. So on average, there isn't a significant difference in runtime between my baseline algorithm and my improved algorithm. On average, it was about 1.3 seconds for the short genome and just over a minute and a half for the longer 1 million base pair genome. I also tested different key lengths. My original optimal key length is 8, and I tested 6 and 10 to see whether it would improve or worsen my accuracy, and I found that it didn't have a big difference. However, when I used a shorter key length, I tended to find more false positives. So overall, there is an improvement. The most dramatic improvement was in the 1 million base pair genome. The accuracy improved by 3 times. Meanwhile, in the shorter genome, it improved by 1.5 times. The great thing is that with the comparing both in both directions to improve the inversion size, both expanding and shrinking the genome, didn't dramatically worsen the runtime. Also, solving several subproblems to solve the larger problem was a major part in improving the accuracy. So currently, this algorithm cannot find inversions longer than length 50. However, the simulator does show inversions up to length 200. So this algorithm can definitely be improved. I think a good way to improve it is to use a method other than SNPs to confine the range where I'm searching. Also, very important is the accuracy of the consensus. Because I'm comparing segments of the consensus to the reference, it's very important that there's no errors in the sequence. So the best way to avoid that problem is to improve my aligning methods. Thank you for listening.